Why do nearly all the planets move around the sun in the same graceful direction, as if following an ancient, unspoken agreement written into the fabric of the solar system itself? If you enjoy quiet journeys through real physics and the deeper stories hidden inside the universe, you are always welcome to gently like and subscribe. And if it feels natural, share where you are listening from tonight. Imagine the early solar system not as a set of finished worlds, but as a vast, dimly lit region of space where gravity was just beginning to organize chaos into form. Long before there were planets, long before there were clear paths traced around the sun, there was a cloud. Astronomers call it the solar nebula, a sprawling mixture of hydrogen, helium, and tiny grains of dust drifting through interstellar space. This cloud was cold and quiet, stretched across trillions of kilometers, and for a long time, nothing much happened at all. Then, somewhere within that cloud, a subtle imbalance appeared. Perhaps a nearby supernova sent a faint shockwave passing through. Or perhaps the cloud simply grew dense enough in one region to begin collapsing under its own gravity. Whatever the cause, once gravity gained the slightest advantage, the story changed. As the cloud began to contract, it did not fall inward perfectly straight. Almost no natural process ever does. Even the tiniest initial motion, a barely measurable drift among particles, became important. As the cloud shrank, those tiny motions were conserved. This is a principle physicists call conservation of angular momentum, and it is one of the quiet rules that shapes the universe on every scale. When an ice skater pulls in their arms and spins faster, they are obeying the same law that guided the birth of the planets. As the solar nebula collapsed, it spun more quickly, not because something pushed it, but because it had nowhere else for that motion to go. Over time, the cloud flattened. What began as a roughly spherical haze became a rotating disk, thin compared to its width, circling around a growing concentration of mass at the center. That central mass would become the sun, igniting nuclear fusion once it grew dense and hot enough. Around it, the remaining material continued its slow, steady rotation, all moving in the same direction, inherited from the original spin of the cloud itself. This shared motion is the quiet reason the planets orbit the sun the way they do. They were not placed individually on their paths. They emerged from this disk, forming out of material that was already moving together, already circling the newborn sun like a river flowing around a deepening whirlpool. Tiny dust grains collided and stuck together, forming pebbles. Pebbles became rocks. Rocks became planetesimals, and over millions of years, gravity gathered these pieces into full-sized planets. Because all of this happened within the same rotating disk, the planets naturally ended up orbiting in the same direction. There was no need for coordination or guidance. The direction was set long before the planets themselves existed, written into the motion of the gas and dust from which they formed. When we look at the solar system today, and notice that most planets orbit counterclockwise when viewed from above the sun's north pole, we are really seeing a fossil record of that ancient spin. The same principle explains why the sun itself rotates in roughly the same direction as the planet's orbit, and why many of the larger moons orbit their planets in matching directions as well. They, too, formed from smaller disks of material, miniature versions of the solar nebula, swirling around growing worlds like Jupiter and Saturn. Everywhere gravity gathers material from a rotating cloud, disks appear, and with them shared directions of motion. Yet the universe is never perfectly tidy. While the overall pattern holds, There are exceptions that make the story richer and more revealing. Venus, for example, rotates backward compared to most planets, and Uranus lies on its side, spinning as if it were knocked over long ago. These oddities do not contradict the original shared motion of the solar nebula. Instead, they hint at later events, colossal impacts and gravitational encounters that altered how these planets spin, even while their paths around the Sun remained aligned with the original disk. To understand why orbit and rotation can tell different stories, it helps to separate the two in your mind. Orbit is about how a planet moves through space around the Sun, while rotation is about how it spins around its own axis. The orbits are ancient, deeply rooted in the earliest structure of the solar system. Planetary rotations, on the other hand, are more vulnerable to change. A single massive collision can tilt a planet, speed it up, slow it down, or even reverse its spin. Earth's own rotation bears subtle evidence of such a history. The leading explanation for the Moon's formation involves a collision between the early Earth and a Mars-sized body. This impact likely altered Earth's rotation and gave birth to the Moon from the debris that followed. Yet, even after such a violent event, Earth continued to orbit the Sun in the same direction as its neighbors, faithful to the original motion of the solar nebula. When astronomers look beyond our solar system, they find the same patterns repeated again and again. Protoplanetary disks have been observed around young stars using telescopes like ALMA, the Atacama Large Millimeter Array. These disks show clear signs of rotation, flattened shapes, and gaps where planets may be forming. In system after system, the expectation is the same. Planets born from these disks will tend to orbit in a shared direction, because the disk itself provides the stage and the motion from which they emerge. This is one of the quiet triumphs of modern astrophysics. By understanding a simple principle like conservation of angular momentum, scientists can explain not only the motion of planets around the Sun, but also the structure of galaxies, the behavior of accretion disks around black holes, and the graceful spirals of matter falling onto newborn stars. The same rule hums softly beneath all of it, reliable and unbroken. There is something deeply calming about realizing that the solar system's order is not imposed from above, but grown from within. The planets did not need instructions. They followed the path already laid down by the gentle, persistent spin of a cloud collapsing under gravity. Even now, billions of years later, that ancient motion continues, carried forward by worlds that have long since forgotten the chaos of their beginnings. As you picture the planets moving together around the Sun, each on its own track yet all sharing the same direction, it can feel like watching a slow cosmic dance that began before memory and will continue long after. The Sun holds them with gravity, but it was motion, quiet and conserved, that gave them their shared sense of direction. And in that steady movement, unchanged across unimaginable spans of time, the early solar system is still present, still turning, still telling its story in silence. That shared motion does more than organize the planets. It quietly stabilizes the entire solar system, allowing it to endure. When objects orbit in the same direction and roughly the same plane, their gravitational interactions tend to be gentle, rhythmic, predictable. Paths cross less violently. Resonances form slowly. The system breathes rather than collides. In this way, the inherited spin of the solar nebula is not only a historical detail, but a reason the solar system remains calm enough for worlds like Earth to exist for billions of years. You can imagine the early disk as a wide, slowly turning lake, its surface made not of water but of gas and dust. Within it, eddies formed where material gathered, and each eddy followed the same overall current. Nothing in that lake was truly still, yet nothing was rushing. The motion was patient. Over time, gravity smoothed the chaos, guiding matter into rings, clumps, and eventually planets, all while preserving the original sense of direction. This same idea explains why most planetary orbits lie close to a single flat plane, known as the ecliptic. It is not that the planets chose this arrangement, but that the disk itself defined it. Objects that tried to move far above or below the plane were gently pulled back by gravity, like leaves settling onto the surface of a slow-moving stream. Direction and flatness emerged together, both consequences of collapse and rotation acting in concert. Even the small leftovers of planet formation still carry this signature. Asteroids in the main belt mostly orbit in the same direction as the planets. The Kuiper belt, far beyond Neptune, preserves a flattened, rotating structure that echoes the ancient disk. Comets, especially those that originate in these distant regions, often follow the same directional flow, though some are nudged into long, tilted paths by gravitational encounters over time. When a comet does arrive from a steep or backward orbit, it stands out. Its motion feels foreign, almost intrusive, not because it violates physics, but because it comes from a region where the original order has been stirred by passing stars and long-term gravitational tides. These exceptions highlight the rule, reminding us how deeply the solar system's shared direction is rooted in its birth. There is a quiet elegance in how little is required to set this pattern. No guiding force needed to align the planets. No later correction was imposed. All it took was a collapsing cloud and the refusal of nature to discard motion. Angular momentum, once present, must be carried forward, reshaped but never erased. It is a promise the universe keeps without effort. The same promise can be seen far beyond our own sun. Spiral galaxies rotate, their stars moving together in vast, flattened disks. Material swirls into black holes through glowing accretion disks, always turning, always conserving motion as it falls inward. Even on the scale of weather systems on Earth, hurricanes spin not because someone instructs them to, but because rotation emerges naturally when forces act across a moving planet. In this way, the planets circling the Sun are not isolated curiosities. They are part of a universal habit, a tendency of matter to organize itself when gravity and motion meet. The shared direction of their orbits is simply the most visible expression of a deeper continuity that runs through the cosmos. As time stretches on, small changes accumulate. Orbits drift, resonances shift, worlds migrate slightly inward or outward. Yet through all of this slow evolution, the overall direction remains. It is astonishingly difficult to reverse an entire system's angular momentum. To do so would require a catastrophe on a scale rarely seen, even in the restless early universe. So the planets continue, quietly faithful to the motion they inherited, circling the Sun as they have for over 4 billion years. When you picture this motion, it need not feel mechanical. It can feel almost biological, like a heartbeat or a breath, steady and reassuring. The planets are not racing. They are moving at the pace set long ago, when a cloud learned how to turn. And in that turning, a structure emerged that would one day host oceans, atmospheres, and minds capable of wondering why the motion exists at all. The answer, gentle and complete, is that the motion was never added. It was always there, faint at first, then amplified by collapse, preserved by law, and carried forward by every grain of dust that became a world. The planets spin around the sun in the same direction because they were born already moving together, and the universe, once it begins a turn, remembers. There is another layer to this story that often goes unnoticed, one that lies not in the large motions of planets, but in the quiet statistical behavior of countless particles. In the early solar nebula, every atom had its own tiny path, its own velocity, its own direction. Yet, when astronomers speak of the disk's rotation, they are describing an average, a collective agreement that emerges when individual motions are summed together. Direction, in this sense, is not imposed. It emerges from many small tendencies aligning, simply because there is no mechanism to undo them all at once. This is why rotation is so persistent in the universe. Random motion can cancel itself out, but once a net rotation appears, even if it is slight, it becomes difficult to remove. Energy can be radiated away as heat or light, but angular momentum cannot vanish so easily. It must be transferred, shared, or redistributed. In the solar nebula, some angular momentum was carried outward by gas and dust that never became part of the sun or planets. Some was stored in the spinning sun itself. Some lives on in the orbits of planets, moons, asteroids, and distant icy bodies. Every piece took its share, and together they preserved the original direction. You can think of this like a long conversation that began before the planets existed. Each collision, each gravitational tug, each spiral inward toward the sun passed the message along. This is how we are moving. This is the direction we carry forward. No voice speaks it aloud, yet the motion continues uninterrupted. Even today, the sun's gravity subtly sculpts this motion. As planets orbit, they exchange tiny amounts of angular momentum with one another. Jupiter, massive and influential, plays a particularly important role, nudging asteroids, shaping resonances, and quietly shepherding the architecture of the solar system. Yet even Jupiter cannot reverse the overall flow. It can rearrange details, but the direction itself is anchored too deeply in the system's history. The exceptions, when they occur, feel dramatic because they stand against this deep-rooted pattern. A planet orbiting backward around its star would suggest an extraordinary past, perhaps a capture from another system or a violent rearrangement long after formation. Such cases are rare, not because they are impossible, but because they require events strong enough to overcome the inherited order of a rotating disk. This rarity becomes even more striking when astronomers study exoplanets. Some distant planetary systems do show unusual configurations, including planets whose orbits are tilted or even reversed relative to their star's rotation. These systems tell stories of instability, migration, and gravitational chaos. They remind us that while the rotating disk is the usual beginning, later events can still rewrite parts of the narrative. Our own solar system, by comparison, appears calm, almost conservative, preserving its original direction with remarkable fidelity. There is something quietly reassuring about that stability. The shared direction of planetary orbits contributes to long-term predictability, allowing climates to settle, seasons to repeat, and orbits to remain nearly unchanged over immense spans of time. Life, at least as we know it, benefits from this patience. The same motion that once gathered dust into planets now allows those planets to remain where they are, circling steadily, rarely surprised. As the planets move, they are not retracing a line drawn for them. They are continuously creating their paths, moment by moment, guided by gravity and inertia together. Each orbit is a balance between falling inward and moving forward. A balance that only works because the direction was set early and shared widely. Without that shared direction, the solar system would be a far more chaotic place, filled with crossings, collisions, and abrupt endings. When you look up at the night sky, even without seeing the planets directly, you are surrounded by this motion. The Earth carries you along its path around the Sun, and the Sun carries all of you around the center of the galaxy. Each level of motion inherits direction from something larger, something older. The idea that planets spin the same way is not an isolated fact, but part of a nested structure of rotations, each one nested inside another like slow, turning gears made of space itself. In this way, direction becomes a kind of memory. Not a memory held by any one object, but a memory embedded in relationships, preserved through interaction rather than thought. The solar system remembers how it began because the laws of physics give it no way to forget. And so the planets continue, circling together, carrying forward a motion that began as a whisper in a cold cloud, long before there was light, long before there were worlds, long before there was anyone to notice the direction at all. There is a subtle intimacy to this idea of cosmic memory, because it means the motion beneath your feet tonight is not accidental. The ground feels still, yet it is traveling through space at tens of kilometers per second, following a curve set billions of years ago. You are moving in the same direction as Mercury and Neptune, as the dust that once drifted between them, as the gas that spiraled inward to form the Sun. The shared direction is so complete that it becomes invisible, like the steady hum of a ship's engine felt only when it stops. Physicists sometimes describe angular momentum as stubborn, but that word barely captures its character. It is not stubborn out of resistance, but out of balance. To remove it, something else must take it away. In the early solar system, there was nowhere for the original spin to go. The surrounding space was vast and mostly empty. The only option was redistribution. The disk spread. Some material drifted outward, carrying excess angular momentum with it. Some fell inward, feeding the Sun. What remained formed planets, each one a compromise between gravity pulling inward and motion carrying it forward. This compromise is stable precisely because it is shared. If one planet drifts slightly, others respond. Gravitational interactions gently trade momentum back and forth, smoothing extremes over time. The direction remains coherent, not because it is enforced, but because it is mutually supported. The planets hold one another in this arrangement as much as the Sun holds them. Even the Sun is not fixed at the center. It moves slightly in response to the pull of the planets, especially Jupiter and Saturn. The entire solar system performs a slow, complex dance around a shifting center of mass. Yet, through all of this subtle motion, the original rotational sense remains intact. Direction survives even complexity. There is a deep physical reason why collapse leads to disks rather than spheres. As material falls inward, motion perpendicular to the axis of rotation is gradually damped by collisions and interactions, while motion around the axis remains. Over time, matter settles into a plane, because that is where it can move freely without constantly crossing paths. The disk is not a coincidence. It is the shape that rotation naturally prefers when gravity is allowed to work patiently. Seen this way, The planets did not simply form in a disk. They are the disk, condensed and refined, each one a place where countless paths converged into a single orbit. Their shared direction is the quiet signature of that convergence. When astronomers model the formation of planetary systems on computers, this behavior emerges automatically. No instruction is given for alignment. The equations of motion take care of it. As long as the starting cloud has even a slight net rotation, the outcome is almost always a rotating disk with planets orbiting in the same direction. The pattern is not fragile. It is robust, resilient, almost inevitable. This inevitability is part of what makes the solar system feel so calm when viewed on human timescales. Change happens, but it happens slowly. The orbits breathe gently over millions of years. Inclinations oscillate. Eccentricities rise and fall. Yet the underlying flow remains steady, like a river that bends and ripples but never forgets which way it is going. It is tempting to imagine that direction implies intention, but physics offers something quieter and more satisfying. Direction is simply what remains when nothing erases it. The universe does not need to choose a way forward. It only needs to remember where it has already begun to turn. In that sense, the planets spinning the same way around the Sun is not a special feature added to our system. It is the most ordinary outcome of matter obeying simple laws over a long time. And yet, when you pause to consider the scale of that time, the delicacy of the initial conditions, and the vastness of the space involved, that ordinariness begins to feel quietly extraordinary. The solar system's shared motion is not loud. It does not announce itself. It simply continues, moment after moment, orbit after orbit, carrying with it the memory of a collapsing cloud and the promise of stability. And, as Earth follows that path tonight, turning and circling in concert with its neighbors, it is participating in a motion that began long before there was a night sky to look up at, and will continue long after the stars we know have faded from view. As this motion continues, it becomes clear that direction is not merely a geometric detail, but a form of continuity that allows complexity to grow without tearing itself apart. In a system where objects move together, small differences can accumulate safely. Worlds can develop surfaces, atmospheres, and histories without being constantly reset by catastrophe. The shared direction of planetary orbits is one of the quiet conditions that makes long stories possible. In the earliest millions of years, the solar system was far less settled than it is now. Young planets migrated inward and outward through the disk, exchanging angular momentum with the surrounding gas. Some were lost entirely, falling into the sun or being ejected into interstellar space. Yet, even during this restless phase, the dominant motion remained aligned. Migration happened along the disk, not across it. The flow had a direction, and even upheaval respected it. This is because the disk itself acted like a guide rail. Gas pressure, gravity, and rotation combined to discourage extreme deviations. Any object that tried to move strongly against the flow encountered resistance, not through friction in the everyday sense, but through gravitational interactions with the surrounding material. Over time, those interactions nudged it back into alignment, smoothing away rebellion and reinforcing coherence. There is a quiet lesson here about how order can arise without force. The solar system did not need to be rigid to be stable. It needed only shared constraints and enough time. Direction was one such constraint, and once established, it shaped everything that followed. As planets matured, their internal structures developed independently. Cores differentiated, mantles convected, magnetic fields rose and fell. Yet, despite these internal differences, their external motion remained synchronized. This separation between internal individuality and external harmony is one of the more subtle beauties of planetary systems. Each world is free to become itself, while still participating in the collective motion that binds it to the whole. Even the slight tilts of planetary orbits, known as inclinations, oscillate gently around the same plane. These oscillations are not signs of disorder, but of balance. Gravitational tugs pull a planet slightly up or down, then back again, like a slow nod. The direction of motion never reverses. It only wavers within bounds, as if testing the edges of its freedom and finding them forgiving but firm. When astronomers reconstruct the early solar system, they find that much of its present calm may be owed to timing. Jupiter formed early while the disk was still rich in gas. Its gravity sculpted the flow of material, limiting the growth of rival giant planets and stabilizing the region where Earth would later form. In doing so, Jupiter helped preserve the system's directional coherence, acting as both participant and guardian in the shared motion. Yet Jupiter itself obeys the same ancient rule. Its immense mass does not grant it exemption from the disk's inheritance. It orbits in the same direction within the same plane, carrying its moons along in miniature versions of the same pattern. Each moon system repeats the story on a smaller scale. Disks within disks, directions within directions, each one a memory nested inside another. This nesting extends outward to the galaxy. The Sun orbits the Milky Way's center, along with billions of other stars, most moving in the same general direction within the galactic disk. That motion, too, traces back to a collapsing cloud, this time on a scale so vast that the mind struggles to hold it. The same physics applies. Gravity gathers. Motion persists. Disks form. Direction emerges and endures. What changes with scale is not the rule, but the tempo. Galactic orbits take hundreds of millions of years. Planetary orbits take years or decades. Atomic motions take fractions of a second. Yet across all of them, angular momentum remains quietly conserved, a patient bookkeeper of motion. This continuity can feel almost personal when you realize that your own body carries angular momentum inherited from the Earth's rotation, which itself is inherited from the early solar system. Every movement you make adds a tiny perturbation to that vast accounting, instantly shared with the planet beneath you. You are not separate from the motion. You are part of it, contributing without effort, carried without awareness. There is no privileged direction in space itself. Up and down, left and right are conveniences of perspective. The direction the planets orbit is meaningful only because it is shared. If the solar nebula had spun the other way, everything would look the same to us, just mirrored. The significance lies not in which direction was chosen, but in the fact that one was chosen at all and preserved. This makes the solar system feel less like a machine and more like a habit. Once established, habits tend to persist, not because they must, but because change requires work. The work needed to reverse an entire system's angular momentum is immense. It would take a collision or encounter of extraordinary scale, something far beyond the gentle environment the Sun has known for most of its life. As a result, the planets continue their shared motion with almost meditative consistency. Their orbits are not perfectly circular, but their deviations repeat in predictable ways. Their speeds vary, but their direction does not. In this steadiness, there is room for subtlety, for long-term cycles that play out over tens of thousands of years, shaping climates and landscapes without ever threatening the underlying order. The Earth's own history is written partly in these cycles. Changes in orbital shape and tilt, known as Milankovitch cycles, influence the advance and retreat of ice ages. These changes occur within the shared directional framework of the solar system, gentle modulations layered atop a constant flow. Without that constancy, such fine-tuned variations would be impossible. When you think about it this way, the planets spinning the same direction around the Sun is not merely a curiosity. It is a foundation. It is what allows time to matter, what allows cause and effect to stretch across eons. It is the reason the solar system can be old without being exhausted, dynamic without being violent. And still, nothing about this motion requires awareness. The planets do not know the direction they follow. They do not remember the cloud from which they came. The memory exists only in the relationships between masses and motions, preserved automatically by laws that operate without intention. This absence of intention is what makes the outcome feel so pure. The order we see is not the result of planning, but of patience. Gravity pulls. Motion persists. Over time, complexity emerges, supported rather than constrained by simplicity. As night deepens, the Earth continues its path, curving through space alongside its companions. The stars appear fixed, but they too are moving, each with its own inherited direction, each part of a larger flow. The universe is full of such motions, layered and overlapping, none of them hurried, none of them wasted. The planets spin the same way around the Sun because they could do no other, given how they began. And in that inevitability, there is a quiet comfort. The cosmos does not rush. It does not forget. It turns, and in turning, it carries everything gently forward, including you, without ever asking you to notice, yet always allowing you to wonder. The longer you sit with this idea, the more it begins to feel like direction itself is a kind of quiet architecture, something that supports everything else without drawing attention to itself. The planets do not merely move around the Sun, they inhabit a shared frame of motion, a reference that gives meaning to before and after, inward and outward, fast and slow. Without that shared frame, motion would still exist, but coherence would not. In the earliest stages of the solar nebula, coherence was fragile. Turbulence rippled through the gas. Shock fronts passed. Density waves rose and faded. Yet even turbulence, when embedded in a rotating system, tends to average out over time. Random motions collide and cancel, while the organized spin remains. This is one of the great filters of cosmic evolution. Chaos can erase itself. Direction cannot, unless something equally organized intervenes. As the disk cooled, different materials condensed at different distances from the Sun. Metals and silicates closer in, ices farther out. This chemical sorting happened within the same rotating flow, meaning that composition varied while motion did not. Mercury and Neptune could become profoundly different worlds while still sharing the same fundamental orbital direction. Diversity grew on top of uniformity, not in opposition to it. This layering is one of the most important patterns in astrophysics. Large-scale order sets the stage. Small-scale variation fills it in. The rotating disk provided the canvas. Planet formation painted the details. When scientists simulate these processes, they often begin with only the simplest ingredients: gravity, motion, gas dynamics. They do not need to specify which way the system should rotate. They only need to allow it to rotate at all. From that single allowance, the rest follows. Planets emerge on aligned orbits. Debris settles into belts. Gaps form where growing worlds clear their paths. The same story appears again and again, not because it is imposed, but because it is preferred by the laws themselves. This preference does not mean inevitability in every detail. There is room for surprise. Resonances can trap planets in synchronized rhythms. Migration can reshuffle distances. Late impacts can tilt axes and scar surfaces. Yet the background motion persists, like a melody that continues even as harmonies change. It is worth noticing how gentle this melody is. The planets are not bound by rigid tracks. Their paths are free-fall trajectories, continuously recalculated by gravity at every moment. Each orbit is an ongoing negotiation between inertia and attraction. That negotiation works smoothly precisely because all participants agree on the direction of travel. If two planets were to orbit in opposite directions in the same plane, their encounters would be catastrophic. Relative speeds would double. Close approaches would become collisions. Stability would vanish. The fact that this does not happen in our solar system is not luck. It is a consequence of shared origin. Even the Sun's equator aligns closely with the planetary plane, a detail that further reinforces the system's coherence. The Sun did not form first and then capture planets. It formed alongside them, from the same rotating material. Its spin is part of the same inheritance, though later evolution has modified it slightly through magnetic interactions and mass loss. The few mismatches that exist, such as the slight tilt between the Sun's equator and the planetary plane, hint at early asymmetries or later influences, perhaps from passing stars during the Sun's youth in a crowded stellar nursery. These deviations are small, not because disturbances never occurred, but because they never overwhelmed the dominant angular momentum of the system as a whole. This tells us something subtle about scale. Large systems are harder to reorient than small ones. A single planet can have its spin altered by an impact. An entire solar system cannot be so easily turned. Its inertia is distributed across vast distances and masses, making its overall direction remarkably resilient. This resilience is one reason the solar system can be understood at all. Predictability is not guaranteed in nature. It emerges when conditions allow. Shared direction is one of those conditions. It allows astronomers to trace orbits backward and forward in time, to reconstruct past configurations, to anticipate future alignments. Without it, celestial mechanics would be far more opaque. The human fascination with planetary motion is ancient. Long before physics existed as a formal discipline, people noticed that the planets moved differently from the stars, wandering yet orderly. What they could not know was that this order traced back to a collapsing cloud billions of years earlier. They saw the surface pattern, not the deep cause. Modern science has gradually revealed that cause, not by intuition but by patience. Telescopes extended vision. Mathematics clarified motion. Experiments on Earth illuminated universal laws. None of these discoveries changed how the planets move. They only changed how we understand why they move that way. Understanding does not diminish wonder. If anything, it refines it. Knowing that the planets share a direction because angular momentum must be conserved adds depth to the sight of the night sky. It turns a visual arrangement into a historical narrative, one that spans from cold interstellar clouds to warm inhabited worlds. The direction itself has no preference. Clockwise and counterclockwise are labels imposed by perspective. If you were to observe the solar system from below its plane rather than above, the direction would appear reversed. The physics would be identical. This symmetry reminds us that meaning in motion comes from relationships, not absolutes. What matters is that the planets move together, not which way they move. Togetherness is the key. It is the difference between a system and a collection. In a collection, objects coexist without coordination. In a system, they influence one another continuously. The solar system is deeply a system. Every orbit subtly affects every other. The shared direction makes these influences cumulative rather than destructive. This cumulative influence allows long-term structures to form, such as orbital resonances where planets fall into repeating gravitational rhythms. Jupiter and Saturn, for example, approach a near resonance that shapes the architecture of the outer solar system. These rhythms depend on shared direction. Without it, synchronization would be fleeting or impossible. Even the delicate rings of Saturn owe their persistence to coherent motion. The particles that make up the rings orbit in the same direction, at slightly different speeds depending on distance. Collisions between them are gentle, redistributing energy without shattering the system. Reverse the direction of half the particles, and the rings would be destroyed in short order. On a smaller scale, the same principle governs protoplanetary disks around young stars. Observations show dust grains settling into thin layers, orbiting smoothly. Within these disks, planets are forming right now, inheriting directions they did not choose. Somewhere, billions of years from now, a listener may look up at those systems and ask the same question you are considering now. Why do all the planets spin the same way? The answer will be the same, because the physics will be the same. There is a quiet humility in realizing how little drama is required to produce such sweeping order. No special conditions, no guiding hand, no fine-tuned intervention. Just gravity, motion, and time. Time is perhaps the most important ingredient of all. The processes that establish shared direction are slow. Collapse takes millions of years. Disk evolution takes millions more. Planet formation unfolds gradually with countless collisions and adjustments. At no point is there a single decisive moment. Direction emerges not in an instant, but through persistence. This slowness is part of what makes the outcome stable. Rapid changes tend to overshoot. Slow changes allow feedback to operate, damping extremes and reinforcing coherence. The solar system had time to settle into its habits. Those habits are still visible today, not only in the orbits of planets, but in the way spacecraft navigate the system. Missions use the shared directional flow to their advantage, stealing tiny bits of angular momentum from planets through gravity assists. These maneuvers work precisely because the system's motion is predictable and aligned. Engineers are not fighting the solar system. They are cooperating with it. In this sense, understanding direction is a form of respect. It is learning how to move with the universe rather than against it. As you remain with this thought, the idea of direction may begin to soften. It stops feeling like an arrow and starts feeling like a current. You are not pushed along this current. You are carried gently, continuously, without effort. The Earth does not strain to orbit the Sun. It simply falls sideways, forever missing its target. That sideways motion was inherited, preserved, and shared. It is enough to keep the planet aloft. to keep days and seasons unfolding in familiar ways. This motion is so reliable that it fades into the background of awareness. Only when you step back, mentally, to the scale of billions of years does its significance become clear. The planets spin the same way because the universe prefers continuity to interruption, because it conserves what it begins, because it allows motion to echo forward through time. And, as this realization settles, it becomes less about explanation and more about orientation. You find yourself placed within a story that is still unfolding, one turn at a time, carried forward by a direction set long before memory, yet still present in every orbit, every night, every quiet moment beneath the moving sky. Over very long stretches of time, the shared direction of the planets becomes something more than a physical fact. It becomes a background condition that shapes how change itself unfolds. Because everything is already moving together, evolution happens through refinement rather than replacement. The solar system does not reinvent itself. It adjusts. In its youth, the sun likely formed within a cluster of other young stars, all born from the same giant molecular cloud. In such environments, close stellar encounters are possible. A passing star can tug at the outer regions of a protoplanetary disk, warping it, truncating it, or stirring distant material. Yet, even under these influences, the inner regions of the disk tend to retain their original direction. The reason is simple and profound. The closer material is bound more tightly. Its angular momentum is deeper, harder to disturb. Direction, once embedded near the center, becomes increasingly difficult to erase. This is why the inner planets show such remarkable alignment. Mercury, Venus, Earth, and Mars all orbit close to the same plane and in the same direction. They formed where the disk was densest and most strongly governed by the sun's gravity. Their shared motion is the most ancient, the most protected. Farther out, small deviations appear, but even there, the underlying direction persists. Direction also influences how matter accretes. When objects orbit the same way, collisions tend to be constructive rather than destructive. Relative velocities are lower. Impacts are more likely to merge material than to vaporize it. This makes growth possible. Planets are not built through violent annihilation, but through countless gentle additions, punctuated by occasional larger impacts. The shared direction of motion is what makes this accumulation efficient rather than wasteful. Without it, early planet formation would be far less successful. Collisions at extreme relative speeds would grind material down rather than building it up. Instead of planets, there would be debris, endlessly shattered and dispersed. The fact that solid worlds exist at all is tied, quietly but directly, to the fact that they all move together. This cooperative motion extends to timekeeping itself. The regularity of planetary orbits provided humanity with its earliest clocks. Years, months, seasons, even long-term calendars all depend on predictable motion. The predictability exists because the system is dynamically calm, and that calm rests partly on shared direction. There is an irony here. The solar system's order emerged from collapse, from a loss of balance. Gravity pulled inward. Energy was shed. What remained was not chaos, but structure. Direction arose not from equilibrium, but from imbalance preserved. This inversion, where order comes from collapse rather than from symmetry, is one of the universe's recurring themes. When physicists speak of symmetry breaking, they often refer to similar processes. A system begins in a uniform state, then chooses one of many equivalent options. Once chosen, that option defines everything that follows. The initial spin of the solar nebula was such a choice. Clockwise or counterclockwise were equally possible. One was selected by chance. After that, chance gave way to necessity. From that moment onward, the direction was locked in, not by decree, but by conservation. Every subsequent interaction respected it. Every planet inherited it. Every orbit reinforced it. This gives direction a strangely narrative quality. There is a beginning, an early branching, and a long, consistent continuation. The story does not need plot twists to remain compelling. Its power lies in its steadiness. Even now, the solar system is not isolated. It moves through interstellar space, encountering tenuous clouds of gas, occasional rogue objects, and the distant gravitational influence of other stars. Yet none of these interactions have been sufficient to reverse or disrupt the fundamental flow. The system absorbs disturbances and carries on. The few objects that do break from the pattern, such as long-period comets arriving from the distant Oort cloud, highlight just how robust the inner system is. These comets can arrive from any direction, their orbits randomly oriented. But they are visitors, not residents. They pass through, interact briefly, and depart. They do not redefine the system's motion. In fact, when such an object does interact strongly with the planets, the outcome usually reinforces the system's existing structure. The comet is ejected or captured into a more regular orbit. Chaos is expelled. Order remains. This selective process has been operating for billions of years. The solar system is not static, but it is self-filtering. Configurations that violate its underlying coherence tend not to last. Shared direction is one of the criteria for long-term survival. From a deeper physical perspective, this reflects the nature of Hamiltonian systems, where conserved quantities constrain evolution. Angular momentum is one such quantity. It restricts the space of possible futures, not by limiting motion, but by shaping it. The planets are free to move, but only in ways that respect what has already been conserved. This idea can feel abstract, but its consequences are tangible. It is why eclipses repeat, why transits occur, why resonances can be calculated centuries in advance, why spacecraft can be navigated with extraordinary precision using gravity alone. All of this rests on the quiet assumption that the system's direction is stable. That stability extends even to the sun's eventual future. As it ages and evolves into a red giant, it will lose mass, altering planetary orbits. The planets will drift outward. Some inner worlds may be engulfed. Yet, even in this transformation, the direction of motion will remain. The system will expand, not reverse. The ancient spin will persist until the system itself dissolves. This persistence across change suggests that direction is less like a feature and more like a constraint, something that shapes possibilities without dictating outcomes. Within that constraint, extraordinary diversity is possible. Worlds can be hot or cold, rocky or gaseous, active or inert. The shared direction does not homogenize them. It simply keeps them connected. Connection, in this sense, is physical, not symbolic. It is enforced by gravity and motion, not by meaning. And yet, meaning emerges from it anyway, because connected systems allow histories to accumulate. As you continue to reflect on this, the idea that all the planets spin the same way begins to feel less like a coincidence and more like a quiet agreement made by matter long ago. Not an agreement in the conscious sense, but an alignment of tendencies that became self-sustaining. The Sun does not command the planets to orbit this way. It merely provides the gravity that makes orbit possible. The direction comes from elsewhere, from the past, from the initial conditions that no longer exist but have never been erased. This is one of the most striking aspects of physical law. The present is never free of the past. It carries it forward automatically. Every orbit tonight contains information about events that happened billions of years ago. The information is not encoded in symbols or records, but in motion itself. Motion, in this view, is a form of memory that does not fade. It can be redistributed, reshaped, subdivided, but not destroyed. The solar system is a memory device on a cosmic scale, storing the fact of its own beginning in the way its parts continue to move. As the planets circle the Sun, they are not just occupying space, they are maintaining a relationship. That relationship is stable because it is simple. It depends on only a few principles, applied consistently over immense time. Simplicity, when given time, can produce astonishing richness. The shared direction of planetary motion is one of those simple conditions that makes richness possible. Without it, complexity would tear itself apart before it could deepen. When you imagine the early solar nebula now, it may no longer feel like a chaotic cloud, but like a quiet turning, barely perceptible at first, gradually becoming the dominant feature of the system. Everything else grew around that turning, adapted to it, relied on it. The planets did not merely emerge from the disk. They are expressions of its motion, condensed into enduring forms. Their orbits are the disk, remembered. And so, even as the universe expands, even as galaxies drift apart, even as stars are born and die, this small local system continues its ancient turn. The direction does not demand attention. It does not announce itself. It simply holds everything together, allowing nights to follow days, seasons to follow seasons, questions to arise and linger. The planets spin the same way around the, Sun because the universe allowed one direction to persist, and then honored that persistence without exception. And, as long as that honoring continues, the motion will remain, carrying the solar system forward, one quiet orbit at a time, unchanged in its essence, endlessly patient, endlessly consistent, a turning that never needs to explain itself to keep going. What begins to emerge, the longer this motion is allowed to persist in your imagination, is a sense that the solar system is not held together by force alone, but by familiarity. Each planet knows, in the only way matter can know, how everything else is moving. That knowledge is encoded in trajectories, in timing, in distance. It is not stored anywhere. It is enacted, moment by moment, as motion unfolds. Because all the planets move the same way, their interactions are predictable enough to be gentle. Predictability, in physics, is not about certainty. It is about bounded behavior. It means that while outcomes can vary, they vary within limits. Shared direction is one of the strongest limiters the solar system possesses. It narrows the range of futures into something survivable. In the absence of that limiter, small disturbances would cascade. A slight deflection could grow into a crossing orbit. A crossing orbit could become a collision. A collision could fragment a world. But when motion is aligned, disturbances tend to spread rather than amplify. Energy is shared. Momentum is exchanged. Extremes soften. This softening effect is why the solar system could pass through periods of intense activity without unraveling. During the late heavy bombardment, billions of years ago, impacts were frequent. Asteroids and comets rained down on the inner planets. Surfaces were reshaped. Atmospheres were altered, yet the orbits endured. The planets kept circling the sun the same way, through chaos layered on top of order. The bombardment itself was likely triggered by migrations of the giant planets, slow shifts in their orbits that destabilized distant reservoirs of debris. Even here, direction mattered. The migrations happened along the disk, not against it. The rearrangement respected the original flow, even as it produced violence on smaller scales. This layering of calm and disruption is one of the most important features of planetary systems. It allows dramatic events to occur without erasing everything that came before. Life, geology, climate, and chemistry all depend on this capacity for selective change. Shared direction is not the only requirement, but it is a foundational one. There is a subtle but profound asymmetry in how nature treats motion and stillness. Stillness is fragile. Motion is robust. A system at rest can be disturbed by the smallest influence. A system in motion tends to carry through disturbances, absorbing them into its trajectory. The solar system's inherited rotation gives it this robustness. It is already moving, already committed to a path, already resistant to reversal. This resistance does not come from rigidity. The orbits are not locked. They are flexible, elastic, responsive, but they are flexible within a shared frame. Like dancers moving to the same slow rhythm, each planet has freedom, but not isolation. Freedom without isolation turns out to be essential for longevity. Completely independent motion leads to frequent conflict. Completely rigid motion leaves no room for adaptation. The solar system occupies a middle ground, and shared direction is one of the reasons it can. As you consider this, it may become clear that the question of why the planets spin the same way is really a question about how systems remember. Memory, in physics, is not mental. It is structural. It exists wherever past conditions constrain future behavior. Angular momentum is one of the most powerful carriers of such memory. The early solar nebula is gone. The gas dispersed, the dust condensed, the environment changed entirely, and yet the direction remains. It has outlived every physical structure that gave rise to it. This is what conserved quantities do. They persist beyond their origins, shaping outcomes long after causes have vanished. In this sense, the solar system is a museum of motion. Not a frozen display, but a living one, where exhibits move and evolve while preserving their essential relationships. The direction of orbit is one such exhibit, always present, never labeled. Even the notion of same direction deserves closer attention. Same does not mean identical. Each planet moves at its own speed, at its own distance, on its own slightly tilted path. Same means compatible. Same means non-opposing. Same means able to coexist without constant conflict. Compatibility is the deeper theme. The planets are compatible with one another's motion because they emerged from a single rotating structure. That compatibility is inherited, not negotiated. It does not require communication. It requires only time and the absence of disruption strong enough to erase it. Time, again, plays a central role. The universe is patient. Given enough time, transient behaviors fade and conserved behaviors dominate. Turbulence decays. Randomness averages out. What remains are the quantities that cannot be lost easily. Direction is one of them. This patience is why astronomers can look at a system billions of years old and still infer how it began. The planets act as tracers, preserving information that would otherwise be inaccessible. Their aligned orbits are evidence, not assumption. They are data written in motion rather than ink. When you hear that nearly all planets orbit the Sun in the same direction, it can sound like a static fact, something that simply is. But in reality, it is an ongoing process. Every orbit renews the fact. Every year, every day, every moment, the system reasserts its coherence by behaving as it has before. If the planets were to stop orbiting for an instant, the fact would vanish. Direction exists only because motion continues. Memory here is active. It must be maintained. The universe does this maintenance automatically without effort, simply by obeying its own rules. There is a quiet elegance in this effortlessness. No energy is spent preserving direction. It costs nothing. It is free once established. The solar system does not work to stay aligned. It simply avoids the rare circumstances that would undo it. Those circumstances, if they were to occur, would be unmistakable. A close encounter with another star, for example, could disrupt the outer system. A massive interstellar object passing nearby could tilt or scatter distant bodies. Even then, the inner planets might remain largely unaffected, protected by the depth of their angular momentum well. Protection by depth is another recurring pattern. What is deeply embedded is hard to change. The planets closest to the Sun carry less angular momentum individually, but they are embedded in a system whose total angular momentum is vast. Their alignment is not a local feature. It is global. This global nature is what makes direction so difficult to tamper with. You cannot reverse one orbit without consequences for the rest. You cannot isolate change. Everything is coupled. Coupling is often seen as a source of complexity, but here it is a source of stability. Because the planets influence one another, none can easily depart from the shared pattern. Deviations are corrected not by force, but by interaction. Interaction smooths. Isolation exaggerates. The solar system chose smoothing, not by choice, but by formation. As you allow this understanding to deepen, the solar system may begin to feel less like a collection of objects and more like a single extended phenomenon. The Sun, the planets, the belts, the distant clouds of ice all participate in one prolonged act of motion. Their differences are real but secondary. The primary feature is the flow they share. This flow is not visible in a single snapshot. It reveals itself only through time. That is why the night sky, though beautiful, does not immediately tell this story. It takes thought, imagination, and knowledge to perceive the motion beneath the stillness. Once perceived, it cannot be unseen. The stars may appear fixed, but you know they are not. The planets may appear scattered, but you know they are aligned. The ground may feel solid, but you know it is moving with extraordinary speed. This knowledge does not destabilize experience. It deepens it. It adds a layer of quiet awe beneath the ordinary. You are not standing still on a static world. You are riding a trajectory that began before Earth existed. You are participating in a motion that required no permission and asks for no effort. The planets spin the same way around the Sun because they were born into motion and never given a reason to stop agreeing with one another. Agreement here is not moral or cognitive. It is mechanical, inevitable, enduring. As long as gravity behaves as it does, as long as angular momentum remains conserved, as long as the system avoids catastrophic interruption, this agreement will hold. That timescale is immense. Long after oceans evaporate, long after continents erode, long after the sun brightens and swells, the direction of motion will persist. It will carry the remnants of worlds outward as mass is lost, preserving the same sense of orbit even as distances change. In this way, direction outlives form. Shapes change, compositions evolve, motion remains. This endurance invites a different way of thinking about permanence. What lasts is not what resists change, but what accommodates it. The solar system's shared direction accommodates change by giving it a framework. Without that framework, change would be destructive. Within it, change becomes history. History, in turn, becomes meaning, at least for beings capable of reflection. The planets do not care which way they orbit, but you can, because that fact connects you to a chain of causes stretching back to a cold cloud in interstellar space. That connection is quiet. It does not demand attention, but it is always present, beneath every sunrise and sunset, beneath every season, beneath every moment when the sky turns and the stars appear to move while you remain seemingly still. The motion continues. It does not announce itself. It simply carries on, preserving direction as faithfully as it preserves distance, allowing the solar system to remain itself, not by resisting time, but by moving with it, endlessly, patiently, and without ever needing to explain why it began to turn in the first place. As this turning persists, it becomes easier to sense how deeply it is woven into every scale of experience, even though it remains far below awareness. The Earth's rotation gives you day and night. Its orbit gives you the year. Both motions are aligned with the larger movement of the solar system, nested neatly inside it. Nothing about your daily rhythm exists outside this inheritance. The simplest act of watching the sky darken in the evening is an encounter with angular momentum that has never been broken. What is striking is how little energy is required to keep all of this going. Once motion is established in the emptiness of space, it encounters almost nothing to slow it down. There is no air to drag against, no surface to scrape along. The planets do not burn fuel to stay in orbit. They simply follow the paths they already have. The cost of maintaining direction is effectively zero. The expense was paid at the beginning, during collapse, when energy was radiated away and motion became organized. After that, the system entered a kind of graceful efficiency that has lasted billions of years. This efficiency is one reason astronomers can treat the solar system as a long-lived structure rather than a fleeting arrangement. Many things in the universe are temporary. Storms fade. Stars burn out. Even galaxies collide and merge. But rotating, systems with conserved angular momentum have a special endurance. They change slowly, predictably, often elegantly. The solar system belongs to this category. When scientists speak of stability, they do not mean immobility. They mean resistance to runaway change. The solar system is stable because deviations tend to remain deviations rather than escalating into collapse. Shared direction plays a crucial role here. When everything moves the same way, disturbances are absorbed into the flow rather than amplified against it. You can imagine throwing a leaf into a slow-moving river. The leaf may spin, drift, or wobble, but it will still be carried downstream. Throw the same leaf into a river flowing equally fast in two opposite directions at once, and no such thing exists. Opposing flows tear structures apart. Agreement, even simple agreement, allows persistence. This analogy is imperfect, but it gestures toward something essential. The solar system's motion is not a balance of opposites. It is a balance of cooperation. Each orbit reinforces the others by sharing the same sense of travel. This cooperation is not fragile. It does not depend on fine-tuning. It depends on the overwhelming dominance of gravity at large scales and the reluctance of angular momentum to disappear. These two facts alone are enough to produce the observed order again and again throughout the universe. When astronomers find young stars surrounded by disks of gas and dust, they are not surprised. When they detect planets orbiting those stars in aligned directions, they are not surprised either. These outcomes are expected because the physics that produces them is simple and universal. What differs from system to system is the level of later disturbance. Some stars form in dense clusters where close encounters are common. Others form in relative isolation. Some disks are massive and turbulent. Others are thin and calm. These differences shape details, not fundamentals. Direction remains one of the most reliable features across all of them. This reliability allows astronomers to make inferences even when direct observation is impossible. If a star shows signs of a disk, it is reasonable to expect aligned orbits. If a planet is found with a wildly misaligned orbit, it suggests a history of strong interactions. Direction becomes a diagnostic tool, a way of reading the past from the present. In this way, the planets are not only moving, they are telling a story, not a story in words, but in patterns. The pattern of shared motion is a sentence written across billions of kilometers, legible to anyone who knows how to look. That sentence says something simple. We formed together. We stayed together. The simplicity of this message is part of its power. Complex systems often leave confusing traces. The solar system leaves a clear one. Its coherence has survived long enough to be unmistakable. There is also something deeply counterintuitive about how calm this all is. The forces involved are enormous. The sun's gravity is immense. The speeds are extraordinary. Earth alone moves through space faster than any human-made object ever has, yet the experience is serene. The calm does not come from weakness, but from balance. Balance here is not static. It is dynamic, constantly renewed. Every moment, gravity pulls inward and motion carries outward. Neither wins. The result is orbit, repeated endlessly. Shared direction ensures that this balance is maintained across the entire system rather than disrupted by conflicting motions. If you were to pause the universe and look only at positions, the planets might seem scattered, arbitrary. Only when time is allowed to flow does the pattern reveal itself. Direction is a time-based property. It exists only through repetition. This makes it easy to overlook. Humans are good at noticing shapes. We are less good at noticing processes that unfold slowly. The solar system's turning is so slow relative to a human lifespan that it fades into abstraction. And yet, it is always happening. This contrast between immediacy and duration is one reason such questions arise at all. Why do the planets spin the same way? Because the answer lives on timescales far removed from everyday intuition. It lives in millions of years, in clouds spanning light years, in motions so gradual they feel like stillness. Once you adjust your sense of scale, the answer feels almost unavoidable. Of course they moved together. They had time to settle. They had no reason to diverge. They formed in an environment that rewarded alignment and discouraged opposition. Opposition, in physics, is expensive. It requires energy, sustained influence, or repeated disturbance. In the quiet region of the galaxy where the sun resides, such disturbance has been rare. The system was allowed to mature undisturbed, and so it retained its original character. This original character is not rigid order, but flowing order. The planets are not locked into a mechanical pattern. They wander slightly. They resonate. They precess. Their paths evolve. But the direction remains a constant backdrop, like a slow tide beneath ripples on the surface. That tide carries everything. It carries dust and rock. It carries oceans and atmospheres. It carries life. Life itself depends on predictability at some level. While variation and change drive evolution, complete unpredictability destroys it. The shared direction of planetary motion is one of the deep physical sources of environmental stability. It ensures that the sun rises and sets in regular ways, that seasons follow seasons, that climates fluctuate within bounds rather than breaking entirely. None of this was planned. It is an emergent consequence of simple rules applied over long time. That is perhaps the most humbling aspect of all. Profound outcomes do not require profound causes. They require persistence. Persistence is what angular momentum provides. Once present, it insists on continuing. Shapes matter into disks, then into systems, then into histories. As you think about the planets moving together, it may begin to feel less like a coincidence and more like a necessity, given the conditions. Not a necessity imposed from outside, but one that arises naturally from the way the universe handles motion. The universe does not like to waste what it has begun. Motion is not discarded lightly. It is redirected, shared, subdivided, but preserved. The solar system is one of the clearest demonstrations of this principle. Every planet you can name, every one you cannot see, participates in this preservation. Even the smallest asteroid carries angular momentum that traces back to the same origin. Even the faintest grain of dust orbiting the sun is aligned with the same ancient turn. In that sense, the solar system is astonishingly democratic. No object is too small to participate. No object is exempt. Direction is not a privilege. It is a property of belonging. Belonging, here, is defined physically. To belong to the solar system is to move with it. Objects that do not are temporary guests. They pass through and leave. Those that remain adapt to the flow. This adaptation does not require awareness. It requires only interaction. Gravity does the rest. As the sun continues its journey around the galaxy, carrying its retinue of planets with it, the solar system itself traces a slow, spiraling path through space. Even this larger motion has a direction, inherited from the rotation of the Milky Way's disk. Once again, collapse, rotation, and conservation have left their mark. The pattern repeats at every scale. Clouds become stars. Stars become systems. Systems become galaxies. Each time, motion is inherited and preserved. Each time, direction emerges and endures. This repetition does not make the universe boring. It makes it legible. It means that understanding one system gives insight into others. The reason the planets orbit the sun the same way is the same reason stars orbit the galaxy the way they do. The scale changes. The rules do not. As this realization settles, the question itself transforms. Why do all the planets spin the same direction around the sun becomes less a puzzle and more an invitation to notice continuity. It invites attention to the way the universe carries its past forward without effort or memory in the human sense. The solar system does not remember consciously. It remembers structurally. Its motion is its memory. That memory is reliable. It does not fade. It does not reinterpret itself. It simply persists, allowing everything built upon it to persist as well. and so the planets continue, orbit after orbit, not because they must strive to do so, but because nothing has ever required them to stop agreeing. Their shared direction is not a command. It is a condition, quietly satisfied, endlessly renewed, holding the system together not by force alone, but by the deep, patient continuity of motion that began long before. There were planets to follow it. Over even longer spans, the persistence of this shared motion begins to feel less like an outcome and more like a condition for meaning itself. Meaning, in a physical sense, depends on repeatability. If nothing repeats, nothing can be compared. If nothing can be compared, patterns dissolve into noise. The solar system's alignment gives repetition a foothold. It allows orbits to recur, angles to cycle, relationships to stabilize long enough to be recognized. This recognition is not limited to human observers. Chemistry depends on stable environments. Geology depends on long-lived heat flows and predictable stresses. Biology depends on cycles that return often enough to be anticipated, even if only implicitly. All of these depend, at some deep level, on the fact that the Earth keeps moving through space in a familiar way, carried by a system that does not surprise itself. The planet's shared direction is one of the reasons surprise is rare on cosmic scales. Surprises happen locally. A volcano erupts, an asteroid strikes, a magnetic field flips, but the framework within which those events occur remains intact. The sky does not suddenly reverse. The sun does not rise in the west tomorrow. Those kinds of reversals would require a violation of the system's most deeply held continuity. Continuity, here, is not rigidity. It is endurance through change. The solar system has changed enormously since its formation. Planetary atmospheres have been lost and gained. Surfaces have been melted, frozen, shattered, and reassembled. Moons have formed and been destroyed. Yet the planets still travel together, direction unchanged, as if the system knows what matters most to preserve. What matters most is not the specific arrangement of worlds, but the coherence of motion that allows arrangements to exist at all. Without that coherence, history would reset constantly. With it, history accumulates. Accumulation is a powerful idea in physics. It is how small effects become large ones. It is how weak forces, given time, reshape entire systems. The shared direction of planetary motion allows accumulation to operate constructively. Small gravitational nudges add up rather than cancel. Resonances deepen. Orbits settle into long-term patterns. Even chaos, when it appears, does so within bounds. The solar system is technically chaotic over very long timescales, meaning that tiny differences can grow and make exact prediction impossible. Yet this chaos is constrained. It does not lead to wholesale disorder. The planets do not suddenly scatter. Direction acts as a boundary condition, limiting how far chaos can roam. This bounded chaos is another subtle gift of alignment. It allows variation without collapse. It allows novelty without erasure. When astronomers model hypothetical solar systems with mixed or opposing orbital directions, the outcomes are telling. Such systems tend to be short-lived. Orbits destabilize. Collisions become frequent. Energy is redistributed violently. Over time, either the system simplifies into a more aligned state, or it destroys itself. Alignment, once again, proves to be the configuration that lasts. Lasting configurations are the ones we get to observe. This introduces a quiet selection effect into astronomy. We see ordered systems not because disorder never occurs, but because disorder rarely persists. The universe may experiment freely, but only certain experiments survive long enough to leave traces. Shared direction is one of the traits favored by survival over time. This perspective can subtly change how the question feels. Why do the planets spin the same way? Because systems that do not rarely endure. What we are seeing is not just formation, but persistence. Persistence is not glamorous. It does not announce itself. It simply continues. Yet without it, nothing complex would remain. The planets are still here because they have been good at continuing. Their shared direction is evidence of that skill. As you sit with this idea, the solar system may begin to feel less like a frozen diagram and more like a long-lived organism, not alive, but exhibiting a kind of structural integrity that allows it to survive its own internal activity. Like an organism, it maintains itself not by resisting change, but by channeling it. Channeling requires pathways. The rotating disk provided the first pathways. Orbits became the enduring ones. Direction defined which paths were viable. Once those paths were established, later additions had to conform. New material arriving from the outer system was captured into aligned orbits or expelled. The system did not accommodate persistent opposition. It filtered it out. Filtering is another way systems preserve identity. They allow what fits and reject what does not. The solar system filters by motion. This filtering continues even now. Interstellar objects occasionally pass through, arriving on hyperbolic trajectories from outside. They come from random directions, bearing no allegiance to the solar system's flow. They pass by once, briefly, and are gone. They are visitors precisely because they do not share the motion. Belonging, once again, is defined by alignment. This definition may feel abstract, but it has tangible consequences. Objects that share the system's direction can interact repeatedly. Repetition allows influence. Influence allows shaping. Objects that do not share the direction are limited to fleeting encounters. The planets have shaped one another over billions of years because they keep meeting again and again in predictable ways. Jupiter's gravity has cleared regions, protected inner worlds, sculpted belts. Saturn has resonated with Jupiter, affecting orbital spacing. These long-term influences depend on repeated alignment. Without shared direction, such relationships would never have time to develop. Time, alignment, and interaction form a triangle that underpins everything from orbital, mechanics to climate stability. Remove anyone and the structure collapses. When you zoom out further, beyond the solar system, the same triangle appears. Galactic disks rotate. Stars orbit in shared directions. Spiral arms persist. The Milky Way itself is a testament to the endurance of rotation. Galaxies that lose coherence often do so through violent mergers. Even then, rotation rarely disappears entirely. It is redistributed, transformed, but conserved. New disks can form from the remnants. Direction reemerges because angular momentum remains. This reemergence reinforces the idea that direction is not fragile. It is resilient. It survives even catastrophe. The solar system has not experienced a major merger since its birth. Its relative isolation has allowed it to remain a pristine example of disk-borne order. That is part of why its structure feels so clean, so legible. Legibility is a gift to understanding. It allows simple explanations to be true. The planets orbit the Sun the same way because they formed from a rotating disk. That explanation works because the system has not been scrambled beyond recognition. Many systems in the universe are not so kind. They require complex histories, multiple stages, and layered explanations. Our solar system, by contrast, still wears its origin openly, written in the direction of its motion. This openness is rare enough to be appreciated. It allows a direct connection between theory and observation. It allows the laws of physics to be felt rather than merely calculated. As you think about the planets moving together, you may notice a shift from asking why to simply noticing that they do. The question gives way to a quiet acceptance of how natural the outcome is, given the rules. Nature does not strive for variety in every aspect. It balances variety with repetition. The solar system shows this balance beautifully. The planets differ enormously, yet their motion agrees. Agreement in one dimension allows freedom in others. Because direction is fixed, other properties can vary widely without destabilizing the whole. This trade-off appears everywhere in physics. Constraints enable complexity. Without constraints, systems dissolve into noise. The shared direction of planetary orbits is one of the most fundamental constraints the solar system possesses. It is also one of the least intrusive. It does not dictate temperature, composition, size, or structure. It only dictates which way to go. That single dictate is enough. It is enough to allow billions of years of history to unfold without interruption. It is enough to allow life to arise on at least one world. It is enough to allow minds to form that can look outward and wonder about motion they cannot feel. You are carried by that motion now, not metaphorically, but physically. Every second, your position in space changes dramatically, even as your experience remains calm. This contrast between inner stillness and outer motion mirrors the larger story. The solar system is moving with extraordinary persistence, yet from within it feels stable. Stability is not the absence of motion. It is the presence of reliable motion. Reliable motion is what the early solar nebula gave rise to when it began to turn. That turn was faint, unremarkable, almost nothing at first. Over time, it became everything. The planets did not decide to follow it. They could not do otherwise. Motion, once begun, carries forward. Conservation ensures that it does. As long as the universe remains governed by the same principles, this pattern will repeat. New stars will form. New disks will spin. New planets will orbit together. Somewhere, perhaps, another world will look up and ask the same question, phrased differently, yet pointing to the same quiet truth. Why do they all move together? Because together is how motion survives. The solar system is not an exception. It is an example of how simple rules, applied patiently, give rise to enduring order. Order that does not constrain wonder, but supports it. Order that does not demand attention, but rewards it. Order that allows a universe in motion to feel, from within, like a place where things can last. As this shared motion endures, it begins to feel less like something imposed from the past, and more like a quiet condition that the present rests upon. The solar system does not renew its alignment each day. It simply never lets it go. The planets wake into motion already in agreement, as if the question of direction was settled so long ago that it no longer needs to be asked. That settled quality is rare in nature. Many systems fluctuate wildly, never quite finding a rhythm they can keep. But rotating systems that conserve angular momentum tend to discover a kind of patience. Once established, their behavior becomes self-reinforcing. Motion that aligns stays aligned because it is rewarded with stability. Motion that does not is gradually filtered away. This filtering happens without intention. There is no preference encoded anywhere for one direction over another. The preference is only for persistence. Whichever direction happens to persist becomes the one that remains. In the case of the solar system, the initial spin of the nebula was enough. It did not need to be strong. It only needed to exist. That faint beginning is easy to underestimate. It is tempting to imagine dramatic rotation from the start, a cloud already spinning rapidly. But in reality, the initial angular momentum may have been barely perceptible. A slight statistical imbalance among countless particles drifting in different directions was enough. Once gravity began to pull those particles inward, that imbalance was magnified. What was once negligible became defining. This amplification is one of gravity's quiet talents. Gravity does not create motion, but it concentrates it. As distances shrink, speeds increase. As clouds collapse, rotation tightens. The same principle that speeds up a spinning skater pulls cosmic motion into sharper focus. Direction, once diffuse, becomes unmistakable. When the sun ignited, it did not erase this history. Fusion did not reset the system. The blazing star at the center inherited the spin of the cloud that formed it, and the planets inherited the spin of the disk that remained. Everything remembers, because nothing has the authority to forget. This lack of forgetting is not philosophical. It is mechanical. There is no mechanism in classical physics that selectively removes angular momentum without transferring it elsewhere. To change direction, something else must take the motion away. In the emptiness of space, there are few takers. This is why the solar system feels insulated, not by walls, but by inertia. Its motion is vast enough that minor disturbances simply ripple across it without altering its course. The planets do not need protection. Their own momentum provides it. Momentum, in this sense, is not just quantity. It is structure. It binds objects into relationships that persist over time. The planets are not merely moving in the same direction. They are moving in ways that remain compatible over billions of years. Compatibility does not mean sameness. Each planet occupies its own niche in the system. Their masses differ by orders of magnitude. Their distances span enormous ranges. Their internal processes are wildly different. Yet none of this disrupts the fundamental agreement of motion. This agreement allows subtle influences to matter. Tides can reshape moons. Resonances can sculpt belts. Small forces, acting over long times, can leave lasting marks. These marks would be erased in a more chaotic system. Here, they accumulate. Accumulation is how history becomes visible. Without it, the past would leave no trace. The solar system's alignment allows the past to speak quietly through present motion. Even the slight tilts of planetary axes, which give rise to seasons, are layered atop this deeper consistency. Earth's axial tilt produces the rhythm of summer and winter, yet that tilt exists within an orbit that never questions its direction. Seasonal change unfolds inside orbital reliability. This nesting of cycles within cycles is another hallmark of rotating systems. Faster motions ride atop slower ones, each inheriting stability from the larger scale beneath it. Days sit within years. Years sit within galactic orbits. Each layer depends on the persistence of the one below. Because of this nesting, the solar system feels legible to the human mind. Patterns repeat often enough to be recognized, yet slowly enough to feel spacious. The shared direction of planetary motion is the deepest layer of that pattern, the one least likely to change, the one that anchors all others. If that anchor were removed, the entire experience of time would unravel. Days might still occur, but they would not be reliable. Years might still exist, but they would not be comparable. The idea of a calendar would lose meaning. Meaning, once again, emerges from regularity. Regularity emerges from conserved motion. This chain is easy to miss because it stretches across domains that are usually kept separate. Physics, timekeeping, climate, biology, and experience itself are often discussed independently. But beneath them all lies the same quiet fact. The planets move together. They move together because they formed together. They formed together because matter collapsed together. And collapse preserved motion rather than erasing it. At no point in this story does complexity need to be invoked. The laws involved are simple. They have been tested in laboratories and confirmed across the cosmos. Their consequences, however, are profound enough to support entire worlds. This is one of the more humbling realizations physics offers. The universe does not require elaborate mechanisms to produce stability. It requires only consistency. Given time, consistency does the rest. The solar system has been consistent for a very long time. That consistency is not fragile. It has survived impacts, migrations, radiation, and internal upheaval. It has survived because its foundation is not a particular configuration of matter, but a conserved relationship among motions. Relationships endure where objects do not. The sun will change. The planets will change. Some will be lost. Others may be altered beyond recognition. But as long as anything remains bound to the sun, it will carry the system's original sense of motion forward. Even in its distant future, when the sun sheds much of its mass and expands, the remaining planets will drift outward rather than reverse. The system will loosen, but it will not turn back. Direction will remain until there is nothing left to carry it. This longevity gives direction a strange dignity. It outlasts names, forms, and functions. It is not tied to usefulness. It simply persists. As you sit with this, the question of why may soften into a recognition of how. How matter behaves when allowed to evolve freely. How motion organizes itself when nothing interferes too strongly. How systems discover stability not through control, but through conservation. The solar system did not choose to be orderly. It became orderly because order was the path of least resistance. Resistance in physics often takes the form of dissipation. Energy is lost as heat. Structures decay. Motion slows. But angular momentum resists dissipation. It has nowhere to go unless something takes it. This resistance gives rotating systems their staying power. The planets are beneficiaries of this resistance. Their shared direction is not enforced by energy expenditure. It is maintained by the absence of mechanisms that could undo it. Absence is an underrated force in the universe. The absence of friction in space allows motion to persist. The absence of close stellar encounters allowed the solar system to mature undisturbed. The absence of large perturbations preserved alignment. These absences are as important as any presence. They are part of the environment that allowed the system to become what it is. When you think about this environment, it may begin to feel astonishingly calm. The sun's neighborhood in the galaxy is not crowded. Stars are distant. Encounters are rare. This quiet allowed the early disk to settle, allowed planets to grow gently, allowed direction to remain coherent. Quiet environments produce long-lived systems. Long-lived systems produce histories. Histories produce meaning, at least for beings capable of reflection. The planets do not reflect. They do not wonder why they move together. But their motion creates the conditions for reflection to arise elsewhere. You are a product of that motion, not symbolically, but physically. The atoms in your body were shaped by processes that depended on orbital stability. The energy that powers your thoughts comes from a star whose light reaches Earth predictably because of shared motion. This connection is not sentimental. It is factual. As the Earth moves through space, it carries everything on its surface with it. You are not stationary relative to the universe. You are tracing an arc set billions of years ago. That arc is smooth. It does not jerk or stutter. It follows the same direction it always has. Smoothness is another gift of alignment. Opposing motions create shocks. Aligned motions create flows. The solar system flows. This flow is not visible in the sky as streaks or trails. It is visible only through understanding. Once understood, it becomes a background presence, quietly reassuring. The planets spin the same way around the sun because the universe values continuity over novelty, not consciously, but structurally. Once motion finds a path that works, it keeps using it. There is no final reason beyond that. No deeper instruction hidden beneath the laws. The explanation does not need to be ornate because the phenomenon does not need to be forced. It is enough that a cloud once turned, that gravity pulled inward, that motion was conserved. Everything else followed from those facts with remarkable patience. The solar system is patient. It does not rush toward an outcome. It simply continues, orbit after orbit, allowing changes to layer gently rather than collide violently. That patience is still at work now. It holds the planets in their paths. It holds the earth beneath your feet. It holds the question itself in a space where it can be asked, considered, and allowed to drift into understanding without urgency. As this long turning persists, it reveals something else that is easy to miss when thinking only in terms of planets and orbits. Direction is not merely inherited once and then forgotten. It is actively reinforced every moment by the balance of forces that keep the system intact. Gravity pulls inward. Motion carries outward. These two tendencies meet and hold one another in place. As long as they remain balanced, direction remains, unquestioned. This balance is delicate in principle, yet remarkably durable in practice. If gravity were slightly stronger or motion slightly weaker, planets would spiral inward. If motion were slightly stronger or gravity slightly weaker, they would drift away. The fact that neither happens on short timescales is another consequence of the shared origin of motion. The velocities of the planets are not arbitrary. They are tuned by formation, adjusted through countless interactions, and then settled into values that complement the sun's pull almost perfectly. Complementarity is an important word here. The planets do not fight gravity. They cooperate with it. Their sideways motion is exactly what allows gravity to hold them without collapse. That sideways motion, inherited from the original disk, is what keeps the solar system suspended in a state of dynamic balance. This is why direction matters so much. Direction is not simply about which way something moves. It is about how forces align or oppose one another. In the solar system, the dominant forces and the dominant motions point in compatible ways. The result is longevity. Longevity allows systems to become layered. Early in the solar system's history, motion was everything. There were no stable surfaces, no atmospheres, no chemistry as we know it. Over time, because motion remained reliable, Other processes could build on top of it. Heat flows stabilized. Differentiation occurred. Magnetic fields emerged. Chemical cycles took hold. Each layer depended on the persistence of the one beneath it. You can think of the solar system as a deep structure with motion at its foundation. That foundation is rarely noticed because it does not change quickly, but remove it, and everything above it collapses. This invisibility is one reason the question arises at all. Why do the planets spin the same way? Because the thing that enforces that sameness is too fundamental to announce itself. It operates silently, beneath events, beneath change, beneath even awareness. The planets do not align themselves each orbit. They simply continue. Continuation is the key. In physics, continuation is often more informative than origin. Many systems have chaotic beginnings, but only some find a way to persist. The solar system's beginning was likely messy, turbulent, and uneven. Its persistence, however, is clean. That cleanliness is what we see when we look at aligned orbits. This difference between origin and persistence is subtle but important. It means the shared direction of planetary motion is not a frozen snapshot of the past. It is a living constraint that has been tested again and again by time. Every million years that passes without disruption is a reaffirmation. Time, in this sense, is not merely duration. It is selection. Configurations that cannot endure are removed from consideration. Configurations that can endure remain visible. The solar system's alignment has passed this test for billions of years. Because of this, the alignment now feels inevitable, even though it was not predetermined. It was one of many possible outcomes at the beginning. It became the outcome that lasted. This distinction matters. It means that the universe does not aim for particular structures. It explores possibilities and retains what works. Shared direction works. It works because it minimizes conflict. It works because it allows energy to be redistributed gently. It works because it permits long-term interaction without destruction. These qualities are not unique to planetary systems. They appear wherever matter organizes itself under gravity. Accretion disks around black holes show the same preference. Material spirals inward in a shared direction, forming stable structures that can persist for long periods despite extreme conditions. Even in these violent environments, direction brings order. Without it, matter would plunge inward chaotically, producing brief flashes rather than enduring structures. Direction stretches events out in time, allowing processes to unfold rather than terminate abruptly. Stretching events out in time is what makes complexity possible. Complexity requires room. It requires duration. It requires the ability for small differences to accumulate rather than cancel. The solar system provides that room by moving together. As you reflect on this, it may become clear that direction is less about geometry and more about generosity. It gives systems space to develop. It allows variation without erasure. It creates a kind of patience in motion. Patience is not often attributed to physical systems, yet here it is, unavoidable. The solar system is patient because it cannot do otherwise. Its motion has nowhere urgent to go. There is no friction demanding haste. There is no target it must reach. It simply orbits. This absence of urgency is one of the most soothing aspects of celestial mechanics. Nothing is late. Nothing is early. Everything happens when it happens and then happens again. Repetition here is not boredom. It is reliability. Reliability is what allows trust. Trust is what allows exploration. Humans could not have explored the sky if planetary motion were erratic. Navigation, calendars, prediction, and science itself depend on the reliability that shared direction provides. This dependence is so deep that it often goes unrecognized. We treat orbital predictability as a given. In reality, it is an achievement of physics, earned through the conservation of motion across immense time. When you watch planets through a telescope, seeing them shift slowly against the stars, you are watching the surface expression of this achievement. The movement appears gentle because it is gentle, not in speed, but in relationship. The planets are not colliding or scattering. They are sliding past one another in a shared flow. This shared flow is why the solar system can be described using relatively simple mathematics. The equations are not simple because the system is trivial. They are simple because the system is coherent. Coherence reduces complexity. Coherence does not mean uniformity. It means compatibility. The planets are compatible with one another's motion because they emerged from the same rotating environment. That environment no longer exists. The gas is gone. The dust is locked into solid bodies. The disk has vanished. But its motion remains, distributed across orbits. This distribution is another important feature. The original angular momentum of the cloud did not end up in one place. It was partitioned. Some went into the sun's rotation, some into planetary orbits, some into the spin of planets and moons, some into distant debris. This partitioning allowed the system to stabilize. No single component carries too much. The load is shared. Shared loads are easier to carry. Because the load is shared, no single event can easily disrupt everything. Even large impacts affect only local components. The global motion remains intact. This global resilience is what allows local fragility. Planets can experience catastrophes without the system collapsing. Life can be extinguished and re-emerge. Surfaces can be erased and rebuilt. The framework persists. Persistence of framework is one of the most important gifts the universe offers to complexity. Without it, beginnings would be endless and endings immediate. As you consider this, the question of why may give way to a feeling of appreciation for how much work this alignment does without being noticed. It is like a foundation buried deep beneath a building. It does not call attention to itself, but everything depends on it. The solar system's foundation is not a physical surface. It is a pattern of motion. Patterns of motion are easy to overlook because they require time to perceive. You cannot see an orbit in an instant. You must wait. Waiting reveals structure. Structure reveals history. History reveals connection. Connection reveals belonging. The planets belong to the sun not because they are captured, but because they move with it. Belonging here is not enforced. It is expressed. As the sun moves through the galaxy, carrying its planets along, the entire system traces a slow curve through space. That curve has a direction too, inherited from the rotation of the Milky Way. Once again, collapse and conservation have left their mark. At every scale, the universe repeats this pattern. Motion begins, direction emerges, and systems that preserve it endure. This repetition does not make the universe dull. It makes it intelligible. The question you began with is not a trivial one. It points directly to this intelligibility. Why do the planets spin the same way? Because intelligible systems are the ones that last long enough to be asked about. This is not circular reasoning. It is an observation about survival over time. Systems that destroy their own coherence do not persist. Systems that preserve it do. The solar system preserved it by aligning motion early and never abandoning that alignment. That alignment does not require constant correction. It requires only the absence of overwhelming disruption. So far, the universe has been kind in that regard. The sun's neighborhood has remained quiet enough. The system has been allowed to mature. Maturity, in this context, means depth. Deep orbits, deep histories, deep connections between cause and effect. These depths are what make reflection possible. As you remain with this thought, the movement of the planets may begin to feel less distant. You are not merely observing a system. You are embedded within it. The same direction that carries Jupiter around the Sun carries the Earth and carries you. This is not metaphor. It is mechanics. Every second, your position in space shifts according to this inherited motion. You do not feel it because everything around you shares it. Relative stillness is the product of shared movement. That shared movement is the reason the world feels stable. Stability here is not immobility. It is agreement. The planets agree on direction because disagreement was filtered out long ago. That filtering continues quietly, ensuring that the system remains what it has always been. A set of worlds moving together, not by choice, not by instruction, but because motion once began, and nothing ever demanded that it be undone. As this agreement in motion remains unbroken, it begins to reveal a deeper feature of how large systems quietly regulate themselves. The solar system does not actively maintain harmony. There is no corrective mechanism constantly adjusting orbits back into place. Instead, harmony emerges because misalignment is inefficient. Inefficiency fades over time. What remains is what flows most easily. Ease is an important concept in physics, even if it rarely sounds poetic. Systems naturally evolve toward states that require the least ongoing effort to sustain. In space, effort usually means energy loss. Motions that shed energy rapidly disappear. Motions that conserve it endure. The shared direction of planetary motion is one of the most energy-efficient arrangements possible for a gravitational system. It wastes almost nothing. This efficiency is why the planets do not spiral inward or fly outward despite constant motion. They are already arranged in a way that minimizes loss. Their paths allow gravity and inertia to coexist without friction. Once such a configuration is found, there is little incentive for nature to abandon it. Over billions of years, this quiet efficiency becomes indistinguishable from permanence. But it is not permanence in the sense of being fixed. It is permanence through motion. The planets remain where they are by moving, not by staying still. This idea can feel counterintuitive, especially in a human world where stability often means immobility. Yet in the cosmos, stillness is usually temporary. Motion is what lasts. The early solar nebula was not calm. It was filled with collisions, shocks, turbulence, and gradients of temperature and density. Yet even then, there was a tendency toward organization. Collisions redistributed energy. Turbulence decayed. What survived was the large-scale rotation, because there was no efficient way to eliminate it. In time, that rotation became the backbone of everything else. It defined a plane. It defined a direction. It defined what kinds of interactions were gentle and what kinds were violent. Gentle interactions accumulate. Violent ones erase. Planet formation depends on accumulation. Tiny grains collide and stick. Pebbles merge into larger bodies. larger bodies attract smaller ones. Each step requires relative speeds that are low enough to allow sticking rather than shattering. Shared direction provides those low relative speeds. If early planetesimals had been moving in wildly different directions, collisions would have been catastrophic rather than constructive. Growth would have stalled. The system might have remained a diffuse cloud of debris rather than condensing into distinct worlds. So, when you notice that the planets move the same way, you are also noticing the reason they exist at all. Direction was not an afterthought. It was a prerequisite. This prerequisite extends to moons as well. Many large moons orbit their planets in the same direction their planets orbit the Sun. These moons formed in smaller disks around growing planets, repeating the same process on a reduced scale. Again, collapse, rotation, conservation, and time worked together to produce alignment. The repetition of this pattern is striking. It suggests that direction is not a special feature of our solar system, but a general outcome of gravitational assembly. Wherever matter gathers and is allowed to evolve without overwhelming disturbance, rotation organizes it. This organization does not require fine-tuning. It emerges robustly from simple beginnings. That robustness is why astronomers trust it. It is why the presence of a disk around a young star immediately suggests the future presence of aligned orbits. Trust in physics is not about belief. It is about consistency. The universe has shown again and again that when similar conditions arise, similar outcomes follow. Direction is one of those outcomes. As the solar system aged, its direction became a reference frame against which all later events were measured. Impacts, migrations, and resonances all occurred relative to the established flow. Nothing happened outside it. This reference frame is invisible but essential. Without it, there would be no meaningful way to describe inclination, retrograde motion, or resonance. These concepts only make sense because there is a dominant, shared direction to compare against. Even the language used to describe orbital motion assumes this background. Prograde and retrograde are defined relative to the system's primary rotation. The fact that most objects are prograde is not an accident. It is the default state. The few retrograde motions that exist stand out precisely because they violate this default. They are clues to unusual histories, captured objects, or extreme interactions. They remind us that alignment is not imposed universally, but earned through formation and preserved through time. Preservation, again, is the key. The planets do not align themselves anew. They persist in alignment because nothing has undone it. Undoing alignment would require either sustained opposing forces or a single, overwhelming event. Neither has occurred in the solar system's history since its earliest days. That absence has been as important as any presence. The Sun's relative isolation in the galaxy has been a quiet gift. No nearby supernovae disrupted the disk after planets formed. No close stellar flybys tore the system apart. The solar system was allowed to grow old gracefully. Grace, here, is a physical property. It describes motion that continues without strain. The planets move with grace because they are not constantly correcting or resisting. They are following paths that suit their environment. Suitability is another understated theme. The solar system's configuration suits the forces acting upon it. It is not optimized in a mathematical sense, but it is well matched. That match is why it endures. Endurance allows layering. Over time, small differences in orbital timing lead to resonances. Resonances shape gaps and clusters. These structures would not survive in a more chaotic system. They depend on reliable repetition. Reliable repetition, once more, depends on shared direction. As you continue to reflect on this, the idea of planets moving together may begin to feel less like a mechanical detail and more like a quiet agreement between matter and time. Matter agrees to move in ways that time can sustain. Time agrees to preserve what matter arranges efficiently. This agreement has no awareness behind it. It emerges from law, not intention. Yet its outcome is something that feels almost intentional in its calm. Calm is perhaps the most surprising quality of the solar system when considered at scale. The energies involved are enormous. The masses are vast. Yet the result is not violence, but order. That order is not static. It is alive with motion. But the motion is coherent. Coherence is what allows the system to be understood without being simplified away. It allows complex mathematics to describe real behavior accurately. It allows predictions to be made and confirmed. Prediction is another benefit of alignment. Because the planets move together, their future positions can be calculated with extraordinary precision. This precision is not magic. It is the consequence of long-term stability rooted in shared motion. Without that stability, the future would be opaque. With it, the future becomes legible. Legibility allows planning. Planning allows exploration. Exploration allows understanding. Understanding, in turn, allows appreciation. As you appreciate the planets moving together, you may notice how little drama the explanation requires. There is no need to invoke rare coincidences or delicate balances. The story is simple because the physics is simple. A cloud collapsed. It rotated. Motion was conserved. Everything else followed. This simplicity is not shallow. It is deep. It operates across scales and across time. It produces outcomes that are rich enough to support worlds and lives. The question of why the planets spin the same way can be answered in a sentence, but living with that answer reveals layers of consequence that unfold endlessly. The answer is not just about planets. It is about how the universe carries its past forward. It carries it not in memory, not in records, but in motion. Motion is the archive. The solar system is one of its volumes. Every orbit is a page turned again and again, unchanged in its direction, quietly reaffirming the conditions that allowed everything else to happen. As the Earth completes another circuit around the Sun, it does not mark the occasion. It simply continues. Continuation is not something the system strives for. It is something it cannot help but do. And in that inability to stop, there is a strange comfort. The motion that began long before there were questions continues without needing answers. It carries the planets, carries the sun, carries you, all in the same inherited direction, steady enough to support wonder, gentle enough to go unnoticed, persistent enough to last longer than any single form that rides upon it. If this quiet journey brought you a moment of calm, a gentle like or a soft tap on subscribe truly helps keep this calm corner of the universe glowing. And tell me, where in the world are you listening from tonight? Rest well until our next quiet journey.